Hello, everyone. Welcome to week one from module one, Introduction to Systems, and section one, System Theory. This week, we are going to talk about systems. We are going to try to define systems, understand the functionality of the systems, and learn about various terminologies and how we try to basically understand system structure and behavior. From next week, we will be focusing on specific form of theories in system science known as complexity science or complex systems. But for now, this week is only about systems in general. Okay, now let's start with the simple question: what is a system? A system is basically a set of interconnected components, also known as elements, that are forming an integrated unit or integrated whole with a specific purpose or functionality. So that definition has various important parts. For example, the interconnections is a key here, as well as functionality or the purpose. So basically, the functionality of a system is defined by its purpose, and usually it's a form of output. In this case, these components, for example, in this schematic that you can see, the components, these circles, are connected to each other with various forms of links. These links can be form of a logical conceptual link, or they can be actual and physical links depending on how we define the system. And these can be very abstract, like information, the transmission from one of these circles or one of these components or elements to another one is a form of relationship, or it can be a friendship like in human society, or it can be a direct pipeline of a petroleum. So this is a system of let's say a petroleum factory, and those are actual pipelines through which we have oil moving from one component to another one. Or these two can be people, and that relationship can be a form of friendship, which is rather abstract type of link, or it can be some form of signal or information that one of these circles sending to another one. So that interconnection forms a structure. It's a very important topic in system science to discuss. And then, as you can see, we have a boundary that the entire system is separated from its environment. The boundary is something that separates our system from its environment. Now, usually, again, if we're talking about physical system, like your house, for example, these walls of your house are physical boundary that you have. Sometimes it's not as obvious. We might be able to use spatial boundaries, like borders between countries are kind of a spatial boundary that we can use. And sometimes it even get more abstract. We cannot define any spatial boundary, and we start using, for example, temporal boundaries, time as the boundary of the system. For example, consider the entire universe, that we cannot really define it as a system with a spatial boundary, because universe entails everything that we have in universe in it. So it's not possible to spatially define any boundary for the universe, but temporally we can say from an event to another, like from Big Bang, how long has passed and things like that, to define the temporal boundary of the system. And sometimes even it is not possible to define system boundary in form of spatial or temporal, and the only way that we can say our system is ending here and another system is starting is just by the level of integrity and integration that our components have, the way they are connected to each other, we know that how they interact with other systems in the environment, and therefore by looking at the structure and the connections, we can say that okay, these type of connections is are among the components of system 1, but then this type of connections are among between system 1 and system 2. Therefore, we can identify where system 1 ends, system 2 starts, and things like that. Other terminology is important here. Obviously, environment is whatever else is that is not in our system. We have inputs and outputs, like inflow and outflow of basically materials or energy and information. We can discuss, and we are going to talk about whether information is a third form of being, existential being, or it's just a property. Some scientists believe that information is a separate form of being. So we have materials, we have energy, and we have basically information. And some believe that no, we only have material and energy, and information is just a property. Nevertheless, whether we believe it is a separate form of entity or not, systems can exchange these with their environment. They can take in materials or deliver materials. They can take in information or energy and deliver information and energy, and that's the inputs and outputs. And finally, stock is another important terminology. It's useful to know about system, which is our inventory, or basically amount of something in the system. Now, some systems have a reservoir for their stock, some systems don't. We do not need a separate part of the system as a storage or as reservoir to stock something, to pile something up in it. Rather, sometimes this system use these connections and links that you see in this scheme as the reservoir or as the storage of the information. So information sometimes, not information, just information, energy, information, material, or anything. So these things that we call them stock can be stored in links among the various components, or they can have a separate reservoir that system pile up and stock whatever the material or energy or information that needed to be stored. So that's the entirety of the system. Now, how we can, or basically what are the important things to consider when we are studying systems? There are 4 important points to pay attention. One is the structure or architecture of the system. We already talked about these components that are connected to each other. So the architecture of the system or the structure is extremely important, as it identifies how system behaves. It is also show us the rules of the game, the rules based on which the system operates, and various components play their role based on that structure. So in fact, these can be very critical with changing 1 or 2 connections or basically anything in the structure, or moving around those components. We can create entirely, completely new and different system. And sometimes if we keep the structure, even if we change all the components, the system is going to be the same. A good example of is this government. Government is a system with a defined structure and architecture, and every 4 years we are electing new people to the office. And in the United States federal level, if you consider everybody has changed with the president, all the basically vice president and the entire government people are changed, and even they start moving federal employees around. So you see, like, in the magnitude of thousands of people changing, but the system, which is the United States government, it stays the same. But sometimes just changing a simple rule, a simple connection, or one component one important component, you can change the entire system, the entire purpose or functionality of the system. And we are going to talk about these when we talk about complex systems. The second important basically consideration to take into account is the mechanisms or the processes that we have in the systems. So basically processes are the steps or things that we do in the system. It's about dynamism of the system. It's the dynamics of the system. If you consider those structures, those links as pipes, this is basically what is flowing inside that pipe. So the mechanism and the process is extremely also important because it has impact on the stock level, on the input level, input flow or the outflow of the system, and it's closely related to the functionality of the system. Depending on how we define the system structure can be also function-based. As we know, functionality shapes the structure. However, the processes are also important because those are the direct link between the system and its outcome or purpose or functionality, and that's why they should be considered. The third important thing, we already briefly talked about it, is the environment which system is located in. And the importance of environment is that it also dictates some external rules to the system, and almost all of the external perturbations are coming from environment. System criticality or some collapses that happen within system, if we take those out, whatever left, all of those perturbations comes from the environment. Therefore, it's extremely important to include environment when we are talking about the system. In other words, you cannot talk about the system in isolation. You should consider the environment as well. And finally, the last part is the functionality or function of the system. As I said, it's to some extent closely related to the output, and it is the purpose of the system. Function or the purpose of the system is that what the system does. And maybe the most difficult one out of these four to identify, because it's not what we talk about, it's not what we say, rather it's what we do. So it should be usually deduced from the behavior of the system and not what we say about the system. So if you want to know what's the functionality of a system, you should carefully study the behavior of the system, which is completely different from behavior of the components that are shaping or forming that system. A couple of important points before we move on to an example about the system is that these components, each of them, and sometimes you have millions of those in one system, these components have their own behavior and their own goals, and many times they even don't know they are part of a larger system. Therefore, their behavior might create issues for the system. And that's unintended consequence or outcome of having many components in the system. So whatever system output is, whatever system functionality and behavior and purpose is, it's not all wanted. Depending on the level of shared vision among these components, some of those outcomes are going to be negative consequences that are also natural consequences, and not always we try to correct them, or even if we can correct them. Another important point regarding the systems is that it's not always about positive things, or for example natural environment or physical environment, like systems we built, like schools, government, and then cars and various machines like the computer or your cell phone. All of these are systems that we created, or we as human being, or most of the animals, the environment, and all the other systems that we have that are intelligent. Not all of them are basically what is intended again. So it's not about just the components that their behavior results in negative consequences. There are systems designed for basically what we call problems. For example, crime systems that are either designed by criminals or just self-organized and form as a result of criminal activities involving various criminals resulted in a crime system. Many of our problems, climate change, um, um, terrorist groups, terrorist cells, and so many other examples that are also systems. So these are two different concepts to consider. One, not all behavior of the components of the system are positive or align with the system's functionality. They can create their own outcomes and negative outcomes. And systems behavior as a whole is not always positive, and even the design of the system is not always positive. So systems sometimes designed or formed as a problem. So it's not that always we look for positive behavior or that type of most of the time we are dealing with issues that are systems themselves. Now, a good example of system that is also in your text is a tree. One tree is a system. It's composed of millions of cells, like human body. So it has these cells have different components in themselves. And even if we zoom out a little bit from cellular level, what we have in tree, you can see here, we have trunk, we have roots, we have leaves, we have whatever we can see and think of is part of the system. Just look at the number of leaves a tree might have. Each of those is a component. Each leaf itself inside that has its own system. We have a system for nutrition that basically feed the tree and help it grow, so that subsystem, for example, consider photosynthesis, is a subsystem in our tree that is helping the tree to feed itself and grow. So if we want to look at this system, which we call tree, it has many subsystems that is also formed of many components, that is structured in a way that form this tree that you can see. So if we look at it from those four perspectives plus the components of the system, the inflow here, you can name a few. Water is one. Nutrition from soil is another one. And so these are the some of the inputs. Sunlight that is needed, carbon dioxide, all of those can be considered input for this tree. And then, and these are just some of them to mention. And then in terms of outputs of tree, we have the oxygen, we have the nutrient, the food for the tree basically. We have elements that it releases, for example, energy in form of heat as a result of activity. It creates heat, so it's also considered an output for the system. And we can think of other things as well. The third one is the structure and architecture. As I said, depending on which subsystem or system you're talking about, or if you're looking from cellular level or what we can see, these can be different. But for example, vessels are a huge part of this system that take nutrients from soil, from the root to the leaves, and we cannot see them. But then at the same time, we can see the leaves, we can see the trunk, and basically branches, and everything that we can see in this image can be considered structure of this system. The mechanism and processes, I already used one of those. Photosynthesis is one of the processes that is turning the nutrients from soil absorbed and transported to the leaves, to the food. And so many other mechanisms that are resulted in how the tree can grow. We are going to talk about a fractal structures. Tree is a fractal structure, and it results in a specific way of this system is growing, basically. In this case, stock can be the level of water. If it is in a dry season, tree is trying to minimize the evaporation in order to keep water. If it is not a dry season, we might increase the intake, at the same time increase the evaporation, and all of those happen based on feedback loop that in the text it explains what type of causal loops we call feedback loop. When it comes to the boundaries, since this is a physical system, it's easy to identify a tree from another one. So you can say when a tree ends and another one starts. In this case, we have no issue identifying the boundaries. And finally, we have the environment, which in this case is going to be a forest or our backyard or street or somewhere that you are going to see this tree in. And finally, the functionality for a tree is survival, obviously, to continue living. But also it might generate some other outputs that you might consider as functionality, interacting with various, for example, insects, birds, and all the other systems around them can be considered as their functionality, producing organic matters and things like that. Now, this tree is located in a forest, which is a larger system. And then we have these forests that are different from each other. We have one forest ends here, and then another forest starts here. So in this case, we have spatial boundaries, which is not as clear cut as the tree itself. If you're not familiar with the landscape, you don't know when you enter to a different forest, when you exited from the previous forest. So still we have those elements that we can talk. What is the boundary? What's the structure, architecture? What's the processes? And things like that. All right. The problem in systems is to understand the system. Understanding system is like the story of the blind man and the matter of elephant, which is an old Indian story, I believe, also mentioned in the poems of Rumi, a Persian poet of Sufism, basically, which is the story of a few blind people touching an elephant, or people that are not necessarily blind but in a dark room touching an elephant, and then everybody, based on what they touch, is giving their own narration. Somebody says it's a rope, somebody says it's a wall, somebody says it's a tree, somebody says it's a spear, somebody says it's a snake, it's a fan. Everybody has their own story because of the limited information they have. We have the same issue when it comes to the system, meaning that our knowledge of the system is to a great extent limited. And this comes from basically two main disconnect in our observation of the system. One is to isolate a system from its environment when studying it, and two is to isolate or to reduce system to its components. And I'm going to get back to these two issues, but before that, if you want to understand a system completely, you have no way of doing it unless you understand the structure and behavior of the system simultaneously. The structure part is the components and their interrelationships, interactions, and the behavior is the behavior of the entire system. And the pattern of the behavior of the entire system. And the system does not need to be an intellectual system in order to create these behaviors. Even systems that created by intelligent beings or systems are themselves intelligent as well. So if you create a machine I'm not talking about computer type of machine, a very simple lever to move things. You can consider that as an intelligent system because created by another intelligent system. So unless it has a linear behavior, which is another form of system, still it's a system. It's not a complex system, obviously, but it's a system itself, no matter what. So structure and behavior, if we don't study these two simultaneously, we are not going to be able to see the entire picture of the system. Okay, so let's talk about the disconnects that I mentioned a few moments ago. For the past 200-300 years, this is what we are doing. Reductionism is the key to science. It's one of the main approaches that in Newtonian systems work perfectly fine. In linear system, it's absolutely working perfectly. And almost all of the science and whatever we have in terms of our engineering and science is a result of that 300 years of reductionism. We break down whatever we are studying to its part, smallest parts, and then we analyze them, and then we put them together, we synthesize it, and that's how knowledge formed. So breaking down to the smallest part, studying it, and then synthesizing it to the original system and understanding the entire system. Now, the problem with this reductionism is that in most of the systems that are not linear, this technique or this approach fails. As a result of this, we have an opposite to this reductionism known as holism, which considers the entire system, the entire thing, instead of breaking it down, instead of reducing an irreducible system to components and studying them, we try to study the entire system. And that's what we call holism. Now, there are two problems with holism. First, it was introduced to the system science community very late. And we didn't have advanced mathematics that we needed to study systems from a holistic perspective. Therefore, most of the techniques we used that we call them holistic are qualitative techniques that are extremely subjective, without any universality, and we cannot basically generalize our findings of studying a system with qualitative approaches. Another issue is that most of the system scientists who start following holism basically start disregarding or rejecting reductionistic approach, which in social science at least resulted to the kind of decline of system science in 1970s, which we will talk about it in a moment. But recently, systemism, which is more common term in social science, appeared that as a technique or as approach that we need both reductionism and holism in order to understand the system. We are in much better place from mathematical perspective right now in order to study the systems from a holistic perspective. And we are going to learn about some of those methods and methodology in this class, but compared to 1970, we are in a much better place. We can quantitatively and objectively study system without a need to break it down to its components. But at the same time, we learned that these two are not mutually exclusive. We can study a system from reductionism perspective. Some of our problems can be solved that way, and some of our problems can be solved only from a holistic perspective and without actually reductionism. So individualism and holism kind of come together in systemism. depending on the type of problem and what we are trying to achieve, we can use either of these two approaches. So this is kind of a common misperception that if you are a system scientist, you are a fan of holism, and you deny or decline or reject reductionism. And finally, some major milestones in system science. The first one was that basically it roots in Golden Age of Athens, very old science, type of science, but its heyday was between 1930 and 1970, relatively recent compared to, even in the story of science, it's relatively recent. And the starting point, there are some debates on this. We have a story that this goes back to a French physicist studying thermodynamic, and thermodynamic is a huge part of system science. We are going to learn it in the complex system section, that still we use thermodynamic studying systems a lot. So that's one side of the story. But equally valid source of the modern approach to system goes back to biology as well. And in fact, Ludwig von Bertalanffy is considered one of the pioneers of general system theory, which is the theory, GST is the theory that severely declined in 1970s, and basically in social science it never recovered from that decline. And it was almost at the same time that we were developing mathematics to study systems from a holistic perspective, not just from a reductionist approach. Although the GTS was significantly declined in social science, we have many theories and components of GST that survived, such as classical system theory. Later on, this became dynamic system theory, computational simulations, that we are going to see how important they are studying systems, set theory, graph theory, cybernetics, control systems, information theory, game theory, queuing theory, and many others that, even if we consider system science as a dead end, all of these have developed their own fields and areas of study. And the last thing is a slight change in disciplines approach to system science, which used to be, so it's kind of rooted in biology and physics, but it used to heavily involved in anthropology and sociology. But after 1970s, and mathematics has always been part of the disciplines, it's the language of it. But since 1970s, we have introduced some other fields, such as computer science, biology and physics, physicist approach or contribution of biology and physics has been tremendously increased, and many other theories new theories that introduced. For example, we have network theory, complexity theory, chaos theory, and dynamic system theory that are all introduced to this area of study. And with that, we conclude our first week overview of the system and system theory. We are starting a very, very important journey in science, and that's approaching our problems and our world from systems perspective. In this course, we are going to learn about complex systems and how they evolve around us, and how approaching these areas from a complex system perspective is going to help us understand them better and in a different way. that we are not used to that. It's going to be new, but at the same time, very fruitful effort to try to formalize system problems and trying to tackle our issues from a systems perspective. Please read all the signed text for this week and see you in next week.